So, what happens, I mean, most people when they hear the idea of radiation, they're scared, right? Because they know that radiation is dangerous, and it can be dangerous, okay? When it strikes a molecule, it can do a number of things. One of the things it can do is it can knock away electrons. The other thing it can do is it can interact with water molecules, and it can make this weird looking ion, positively charged water, which is very undesirable and very reactive, and that causes bad stuff to happen. And so, welcome ladies. So cells are most sensitive to radiation are ones that undergo rapid cell division. Where do you have rapid cell division? In your bone marrow. What do you do in your bone marrow? Why do you have rapid cell division in your bone marrow? It's where you make your red blood cells at, right? Your body's constantly making red blood cells. So if you damage your bone marrow, you wind up with a form normally of leukemia, right? It's not good, okay? The other really common place besides the skin is reproductive cells, right? Particularly for males, because our reproductive organs are exposed, right? Easy for radiation to hit them. So what happens? Well, if you make those water ions that we showed before, and they react with something else, they damage the DNA in those cells, and then what happens? That gets transferred to your offspring, right? And that's why after Hiroshima and Nagasaki, there were so many kids born with what? Genetic defects. Why? Because the parents were exposed to radiation and damaged their reproductive organs, particularly the males. Okay. That's why when you go and have x-rays taken, they cover parts of your body, right? So, how do you protect yourself from radiation? Well, it depends upon the type of particle that you're trying to protect yourself from, okay? If you're trying to protect yourself from alpha particles are big guys, right? Can be protected by just using paper or clothing, right? Because they're so big, they're going to hit anything that's in their way and they'll just stop right there. Beta particles, smaller, high energy, but they can still be blocked by just using gloves or lab coats, right? They'll block most of those. Now, gamma rays are the bad boys because they don't have any mass. They're just a high energy wave. So you have to have something really dense to block gamma rays. In particular, a lead shield, right? Okay. And so that's why, like when you go and have x-rays done, it produces some gamma rays, and so that's why they cover you with a lead shield. Okay. The other way to prevent problems with radiation is just limit how much time you're exposed or increase the distance from the source. How do you know how long you've been exposed? Anybody here ever worked in a lab where you had to wear a little badge for radiation? Dental hygienists wear them all the time, right? Because if you're exposed too much, then what happens? Then you can have damage, and so that little, it's called a dosimeter. You send it off to the lab every now and then, or if it starts changing colors, then you know, hey, I've been exposed for too long. I should limit my exposure, right? I shouldn't be exposed so much.
Well, what is considered too long? Does it vary?
It varies on the type of radiation that you're exposed to, yes. So. It also depends upon your mass. So, if you work in an environment where you have radioactive materials, the idea is not to spend much time there and to wear the appropriate clothing, right? So you can wear a good lab coat and gloves that cover most of your body that are protected from alpha and beta particles. The big nasty is gamma rays, right? For those guys, you really have to work with lead shielding all the time. You want lead between you and the source, okay? Because it's constantly giving out gamma rays, okay? Or you can just move far apart. The problem is if you're working with gamma rays, you have to be 500 meters away from it to be safe. How far is 500 meters? I know? 5 football fields, roughly, right? That's a long way. Just campus isn't 500 meters wide, right? okay? So it's like the distance probably from like here over to Lee Senior's football stadium or something, right? Pretty long ways. Okay, that's how far gamma rays travel. The alpha and beta particles don't travel very far because they're relatively large. They interact with other things. Let's get this. So, let's talk for a few minutes about nuclear reactions. I told the other class there won't be a bunch of questions on nuclear reactions. There may be one or two where you have to write them. Now, the key here in writing a balanced nuclear equation is that the elements might change from reactants to products, but what's true? The mass has to always be constant. Okay? So let's think about it. Let's do a couple. Let's look at this example they have right here. Here we have californium decaying to give curium. Okay? Look at the number of protons, or look at the mass number on the left and the mass number on the right. On the left-hand side, californium has, this particular isotope has a mass of 251. If I sum on the right-hand side for my products, right, I get 247 plus 4 gives 251. Now, also is true for the atomic number. Here I have 98, right? Ooh, 98. Really? If I add 96 and 2 together, I also get 98. Okay, this is always true. So let's do a couple more. So here we have, hope you have your periodic table because these are all elements that you don't deal with very often. Here we have americium going to decay by alpha emission. All right, let's look. First thing let's figure out what the number of protons is over here in this new element. What do you think the number of protons should be in a new element? We start with 95, we ejected 2, so it's got to be 93. And which element is 93? And the symbol is NP? All right, what's the mass number for this element, for this isotope?
237.
Why 237?
Because it needs to equal 241.
Because it has to equal 241. So 4 plus 237 gives 241. And on the bottom, 93. 93 plus 2 gives 95. Everybody see how I do that?
Yeah.
That's pretty straightforward, huh?
Don't. Please.
Look, I'm gonna give you the answer. Right there. You can actually read this one. You couldn't read mine.
I can read your spot. I just like to see it, so I can do it at home.
You good?
Yeah.
Okay. What about when we have beta decay? But look at it now. We're going to give off -1 in the atomic number. That means that the new element must go up by 1 in the atomic number. Down here, let's write this one bigger. So we have C14 going to give okay. Let's look. Do our mass numbers sum? On the left-hand side, our mass number is what? What's our mass number on the left-hand side?
14.
And what's our mass number on the right-hand side?
14.
14 plus 0 is still 14. All right, what's our atomic number on the left-hand side? 6. And what's our atomic number on the right-hand side, on the product? Still 6. 7 plus -1 is 6. Okay? So when you have beta decay, note that we get a new element, just like before, except now the atomic number goes up instead of going down. Goes up by 1 because we lost an electron out of the nucleus. Okay? Does that make sense? A little bit? There's not going to be a ton of these. Let's try this one together. Here we have potassium decaying, okay? Let's predict what the new element's going to be. What's the atomic number going to be on my new element? 20, because 20 plus negative 1 gives 19, doesn't it?
That's calcium.
And that is calcium, okay? What's the mass number on this new isotope?
42.
It's still 42, because 42 plus 0 gives me 42. Okay? What do we say? The mass numbers on the left have to match the sum of the mass numbers on the right, and the atomic numbers on the left have to match the atomic numbers on the right. Okay? So 20 minus 1 gives 19.
And you know the element of calcium because calcium is
Element 20.
element number 20 on the chart.
Yep.
Okay.
That seems pretty easy, huh? We could all do that? Well, then do this one. Write a nuclear equation for this, for the beta decay of cobalt 60. Are we ready? So what's my atomic number going to be?
28.
Has to be 28, right? Because 28 minus 1 gives 27. And element 28 is
Nickel.
nickel. And the mass number is
60.
60, does not change. Positron emission is very similar to beta decay, except that what happens? Now the atomic number does what? It goes down one, right? Because this is a positive number, so these two, 24 plus 1 is 25. Note the mass number stays the same. It's very similar to what we just did, except that the atomic number goes down. So if cobalt 60 decayed by positron emission, it would go from cobalt to, what's the next element down from cobalt? It would go to iron, right? If it decayed by positron emission. It doesn't, but just if. The last form of radioactive decay is gamma radiation. And there's a new symbol that we haven't used before, this guy right here. We've never put an M right here before, have we?
No.
This M just simply means that this is an unstable nucleus. So look, the difference between here and here is all we did was get rid of the M. Technetium-99 with this M here means it's unstable, and it gives off a high energy gamma ray, and now it's a little bit more stable. Still not stable, but more stable, okay?